welcome everyone to the latest webinar in the Smart Semiotics series. Today, we're really pleased to introduce Professor Jean-Guy Meunier to talk with us today. We also have quite a large panel of people who are going to be responding to the presentation. So Professor Meunier works at the University of Quebec in Montreal in the program of philosophy, semiotics, and cognitive informatics. And he's a member of the International Academy of Philosophy of Science. He's very well recognized as a pioneer in the field of digital humanities, and actually received the Canadian Digital Humanities Prize for his achievements in this area. He's published over 150 articles related to computer-assisted text analysis, semiotics, and digital humanities, and very recently published a book titled Computational Semiotics with Bloomsbury Academic. And he'll be talking to us today on the topic of can semiotics become computational? And I think with that, I'll just hand over and we can get started. So Jean-Guy, if you'd like to begin.
Thank you, Andrew Wardell, for this sharp introduction. I must also thank WISAC, this Eternal Semioticians, for this prestigious invitation. And I thank all the panelists for being present here at different times and from different places throughout the world. Unfortunately, because of a limited bandwidth with my Wi-Fi, I will have to cut you off the cameo of my face and leave you, I hope, with the pleasure of my voice. I thank you all for being attentive to my research question. It has been a daunting question for me throughout my career, and I hope and I believe that it has been also a daunting question for many semioticians. So this question is, can semiotic be computational? In 2009, Bungart and Stenfeld undertook an investigation into the future challenges of semiotics by interviewing different competent and expert semioticians. The conclusion of this study was clear. Semiotics would be renewed by the power of dominant structuralism. This paradigm was seen as a more rigorous approach than that offered by classical philosophy and semiotics. In 2014, Cole and Velmimosa took over this investigation, interviewing another group of semioticians. But this time the results were very different. The main complaint was that structuralism had not delivered the expected rigor, and it had not really explored formalizations of the notion of structure. Semiotic remained mostly analytical, conceptual, and speculative. Unfortunately, the role of computers had not been investigated as such. Today, some new answer to the state of semiotics may be found by understanding more the relations of semiotics to computers. Indeed, the introduction of computers in the field of all natural, social, and human sciences has a great impact in many disciplines. It has often influenced what science studies as objects and how they study these objects. It seems obvious that semiotics cannot resist the introductions of computational paradigms in their field. It will surely affect both its object and its methodology. So this raises our important research question: can semiotics become computational? The relation of computers to semiotics is not new. In the last 40 years, a few research programs invited semiotics in the realms of computers. A first such program had been proposed by the Russian computer scientist Pospolov. He had hinted that semiotics would be a great meta theory for understanding computers. Still, it was Newell and Simon who were the first to create such a research program, and they stated explicitly, although without any overt reference to semiotics, that computers were to be seen as physical symbols manipulating systems. Naden stated just a few years later that computers are semiotic machines driven by semiotic engines. And Irvine just lately reformulated in slightly different terms. Computing systems are intentionally designed semiotic systems. Unfortunately, as one may guess, this semiotic paradigm was not easily accepted in the computer science community. Nearly 20 years later, a second research program explicitly applied semiotics to various computer components. It was the beginning of what was called computer semiotics. Computer inputs and outputs interfaces were the first such components described as semiotic systems, and many other components followed. About the same time as the last program, a third research project emerged and was this time explicitly called computational semiotics. But here, semiotics was again applied to computer systems. These systems were much more complex, though. They were to be dynamic, adaptable, and open systems. A fourth computer semiotic research program explored directly the heart of computers. It mainly studied its program and its algorithms. It saw computer systems as a special type of dynamic semiotic system, embedded with a syntax, a semantics, and a pragmatic control. Finally, some other research project inserted semiotics into computational information systems. A last and important such research program called digital semiotics was quite different from computer semiotics as such. It studied a variety of computer-created artifacts. Digital semiotics has now 40 years of highly interesting publications by numerous semioticians. As we can see, these research programs all propose an encounter of semiotics with computer systems. But technically speaking, these research programs go in a specific direction. They apply semiotics to computers. They are analogous to other scientific research programs that can study aspects of computers such as economics of computers, linguistics of computers, history of computers, and philosophy of computers. So semiotics of computers, or computer semiotic, is a totally acceptable research inquiry. But one may ask if the research direction may be inversed. That is, could computation itself be applied to semiotics? In other words, can there be a computational semiotics? Just as computation is applied to specific practices, like in computational economics, computational history, and even computational philosophy. At first sight, such a research program seems a paradox. Indeed, how could an interpretive paradigm seriously dialogue with a naturalist paradigm? Are we not locked in the classical opposition of Geistwissenschaften or Naturwissenschaften? Because these words, computation and semiotics, are so different in their semantics, this raises a paradox. Our intention here is not to resolve this paradox in itself. We can only begin untightening its internal tension by examining how some of these tasks may share some common features. But to do this, we must modify the conceptuality that necessarily created this paradox and seek some epistemological fresh air. The fresh air will come from contemporary philosophy of science. This will allow us to see how it is possible and under what conditions semiotics may become computational. Traditionally, science is understood as an epistemic endeavour, whose main role is to build theories. And these theories are classically defined as a type of knowledge that is expressed in a set of explanatory, nomenological, formal statements or laws. But as we know, this vision of science has been under high criticism. This vision, though, of science is highly reductive. One of its main critics is that such a type of scientific practice can retain only a small set of features of the phenomenon under study, and it makes it difficult to deal with complex phenomena such as the ones dealing with meaning and intentions. Secondly, as research shows, even in natural sciences, despite its highly praised public image, such scientific practice with these highly restrictive conditions are rarely found. Therefore, it immediately appears as an inadequate epistemological grounding for semiotics. In contraposition to this reductive vision of science, some contemporary philosophers of science have proposed to see science in a more pragmatic way. Here, science is seen as a complex cognitive endeavour which rests on many and various interconnected statements, all of which are defined as a different point of view on the object under study. These points of view have been called models. In this perspective, scientific theories are aggregation and integrations of a multitude and variety of models. Therefore, models are epistemic artifacts that offer different views on a phenomenon. And in this view, models are not just vague hypotheses, but specific explanatory statements. Some provide descriptions and means of understanding the research object, the method used, the evaluation, and the interpretations of the results. They always have multiple forms of expressions, though. Some statements produced are formal, others non-formals. Some use algorithmic, graphic, or iconic languages, but most of the times they are expressed in natural language and even in ordinary daily language. Finally, these models are interrelated and diverse. But each of these models, as it is often formulated, is an epistemic mediator for knowing the world and how we think of the world. Finally, they are used to communicate with members of various epistemic communities. It turns out that this pragmatist paradigm is one in which computer scientists themselves define their own scientific research practices. That is, computer science is a modeling engineering practice. This is important for understanding computational semiotics because it involves computer system. Computational semiotics must also be seen as a modeling engineering practice. This may be shocking for semioticians, but if well understood, this hypothesis will allow us to determine under which conditions semiotics can become computational. Let us now illustrate this model engineering view of science in a few pedagogical examples. Our first example is the set of models for building a computational simulation of a tornado. At least 4 models are needed. A conceptual model will describe the main problem that a computer system simulating a tornado will have to deal with. It will have to build natural language statements on the main features of this natural phenomenon. The formal model, for its part, will translate selected subset of these concepts into mathematical formal statements or equations, from which some experimental observation will ultimately serve as validations of these equations. The computational model for itself will translate these formal statements into algorithms. Finally, the physical models will, in turn, implement these algorithms in an electronic calculating machine called a computer, where some interfaces may present on a screen some visualizations of the changes of values or other variables involved in the computations, such as the movement of the tornado, its speed, its force, and so forth. Ultimately, the results of these three last models will be interpreted and understood in regard of the original conceptual model, and it may be expressed in a natural language. Similar type of model have been built for this tic-tac-toe computer game. Here too, at least 4 models have to be built. The conceptual model must explain the aims and the rules of the game. A second model will define formally some of these components, for instance, by a grammar. The third model will translate these formal models in effective computational procedures or algorithms. And finally, a physical model will implement them in a computer technology. In other words, in many scientific projects where computers are involved, we can distinguish at least these 4 main models. They each can be subdivided into many other submodels. They are also interdependent, interactive, and cyclical. As the topic of models is a complex and sophisticated domain, we will hereafter present in an illustrative and hopefully in a synthetic manner how each type of models intervene in a computer systems. Naturally, these models become essential in a computational semiotic project. A first and essential type of model in all computer projects is the conceptual model. The main role of conceptual models are the following. It identifies, describes, and conceptualizes the various components and features of the object, the task to be realized. It makes decisions related to the method, its application, its evaluation. It builds communication tools among the stakeholders of the research or the members of the epistemic community. It explains and interprets the research process and results. Its semiotic expression is mainly natural language, but it may take other semiotic forms such as iconic or even directed graph. And in a computer project, it may take semi or complete formal models of expressions, such as ontologies, knowledge graphs, and so forth. It will call upon complex and high-level cognitive operations, such as abstraction, idealization, inferences, generalizations, individuation, inductions, abductions, deductions, and so forth. Finally, it contains biases, beliefs, cultures, theories, practices, know-how, and so forth. In various disciplines, although with some variants, conceptual models come under many names and contents, such as conceptual spaces, conceptual systems, mental models, tacit knowledges, conceptual schemas, ontologies, knowledge representation. But in computer science, it is explicitly called a conceptual model. In short, a scientific knowledge project, more so a computer-assisted project, cannot be just a set of mathematical equations or logical formulas with their translations into algorithms. And as Gaston Granger states it so well, formalization is only one horizon in the scientific thought. Here is a simple example. Imagine that a research project aims to build a digital grandfather clock. there could exist many conceptual models describing and explaining what is and how this artifact works. One could describe technically the pendulum as such. Another model may focus on the timekeeping gears. Another one could describe the overall functioning in a household. English could be the preferred language for expressing the concepts involved in these conceptual models. And depending on the research objective, only a very small set of conceptualized features will be retained for a formal model. But all three participate in the ultimate understanding of this timekeeping technological artifact. Scientists eventually dip in their conceptual background to translate their formal models into some easier understanding of their whole theory. And this translation may go quite far in the natural language discourse. It may use highly simple daily example or deep philosophical concepts. All may express them in metaphors, metonymies, semantic blending, fictions, narrative, and so forth. Naturally, this use of natural language suffers of all the problems of semantic ambiguity, implicit or non-constrained inferences, underlying biases, and so forth. As any other computer projects, a computational semiotic project must build a conceptual model that determines the pertinent concept related to its object and to the task to be realized. This may call upon some semiotic theoretical background, some important meaningful features or semiosis processes involved in the analysis of the operations going on in the project. But this is not an easy task. It is not as easy as one may think. Take, for example, the complexity of building a conceptual model of the semiotic features and semiotic analysis operations underlying this small set of photo of known state leaders. This task cannot be delegated to a computer, for it would mean that the computer knows ahead what are some of the main and most important features of these artifacts that ground their meaning and how they can be processed. Here is another example. What are the meaningful features that in musical scores of Xenakis, Varese, Penderecki, Mondrot could be the input for a formal computational model? This is not an easy task, mainly if the corpus runs in the 1,000 pages. Detections of certain irregularities in the pixels may be useful for some search and recall purposes, but their pertinency for a rich and interesting semiotic analysis task is very low. Throughout this presentation, we will illustrate our model's hypothesis on two sets of semiotic artifacts. The first one is a collection of iconic signs forming 148700 artworks of René Magritte, and the second one is a subset of Peirce's symbolic signs forming a text of 50 pages called the Collected Papers. The role of conceptual model in this first experiment is to identify the most pertinent iconic features of each Magritte artworks. In the actual state of the art, a computer can only identify very classical, mundane, prototypical meaning forms, such as a pipe, a bird, a hat, a tree, and so forth. It would not be sensitive to artwork's aesthetic structure, such as the composition, the texture, the economic value, and so forth. Another important role of the conceptual model here is to identify in these features the methods to be used in their analysis and reveal whatever is the underlying semiotic theoretical background and offer some evaluation and interpretation parameters. For the actual description constructed for each artwork, we have used the complete and detailed handmade thematic annotations produced by Hebert and Gravel on the Magritte artwork published in the David Sylvester catalogue Raisonné. Each artwork was annotated or tagged by some 10 to 15 features, all of which were chosen in relation to the Saussurian differential semiotic view of meaning. They are here represented by some color differential geometric forms. In the second experiment, the Peirce collected papers, the conceptual model identified the most pertinent semiotic features of this symbolic semiotic artifact. These were the words, the segments, the pages, the titles, and so forth. The words were reduced to their basic morphological form or lemma. The segment was a sequence of chosen number of such words. Many other features could be identified, such as rhetorical, textual, discourse features, and so forth. These features are again represented here by a geometrical colored font. The conceptual model also contains statements about the objective and methods of conceptual analysis or philosophical concepts that was to be explored in this experiment. The second model for building a computational system is a formal model. In a classical vision of science, it is seen as the core model of scientific practice. One must recall here that a formal model is always defined as a set of symbols manipulated by a set of rules. In practice, it may take the form of a logical formula, equations, grammars, graphs, and so forth. But most importantly, we must recall here that, by definition, formal models are without semantics. Naturally, a semantic must be added to such formal models, but it will be given to it by external means. In computer science, these symbols are said to be interpreted symbols. The classical and intuitive understanding of the meaning of these formal statements in a formal model has regularly been explained, and more so today, in terms of something representing something else. The understanding of this concept or representation is often expressed by using a metaphor. A representation is like a mirror that reflects something in the world. Carnap, Tarski, Kripke, Van Frassen, and many others have offered a formalization of this representational notion. A representation is a relation between symbols and some type of states of affair in an actual world or possible world. Although very rigorous, this formal representational view of scientific formal models has been highly criticized. It is too reductive and not easily adaptable for complex phenomena. For instance, it has difficulty to take into account the situations, the actor, the purpose, the culture in which sciences emerge and are used. And when formalized, this would mean that you need to add more and more variables, constants, and operations into the formal model, which in turn would induce a great complexity in its structure, uses, and application, mainly if the model aimed at covering all cases and would be exhaustive. And consequently, it's the verification and validation of formal models through observation or experimentation that becomes quite a task. But there exists, however, a radically different way of thinking about the semantic or formal models, where the concept of representation is thoroughly different. A first view, often not recognized for its originality, comes from Peirce. In a forthcoming paper, Martin Irwin has shown that Peirce, in his late unpublished papers, had developed another understanding of the concept of representation. As we know, for Peirce, the classical definition of a representation is always something that stands for something else and for somebody. In his later papers, this understanding of the stand for relation, in the case of a formal representation, is no more thought as a reflection or a mirror of something. Rather, it is understood as something that somebody maps onto the world. It is a one-to-one relation, that is to say, it is an homological relation. The signs chosen are something in the world. This means that we should understand symbolic formal systems or models as something mapping something on the world and always for somebody. In other words, a formal model organizes our point of view so that it points to the world in a one-to-one relation. A similar idea has also been expressed, but surely in a more mathematical way, by the Bourbakis group, for whom a formal model is not a representation in the classical sense. Rather, formal models use mathematical structures which, for Peirce, are mapped onto the world, but for Bourbaki are projected onto the world. But these mathematical structures are not, as in a constructivist view of mathematics, built a priori by the mathematicians. In a metaphorical way, we can say that the Bourbakian mathematical structure expressing properties and relations are thrown on whatever is the object under study. They are not mirrors of the world or of the object under study. We could even say that they are filters projected on the object under study. They therefore retain only some specific types of features in relation on whatever they are mapped on. It also follows, according to Peirce, that this mapping or projection is intentionally built by a user. But if a project involves a computer, the formal model will necessarily retain just some limited features or properties among the myriad other ones that conceptual models may identify and describe. These features chosen will become what the symbols of the variables, constants, operators, predicate designate. But if the semantic of these symbols is not embedded and shared in a rich conceptual model, there is no explanation and understanding of the phenomenon. For instance, if one cannot interpret the symbols of the formal models casted for our grandfather clock, nothing is understood. This is what Duhem stated so neatly. This is why science needs conceptual models expressed in a natural language. A nice example of this question are formal presentations of a linguistic grammar, such as the ones formalized in Chomsky's generative formalism. These are formal models that are casted on the language phenomenon. They are not mirrors of the language. Chomsky has shown that there are equivalents between many other formal models. For instance, between some types of generative context-free grammar and the automata models of von Neumann, or some post-grammars or some Markov algorithms. It does not follow, though, that a linguist knows how to translate these rules into algorithms. The same type of argument can be applied to artificial intelligence projects. For instance, the matrix, presented here on the left, is one among many others that artificial intelligence projects can use for representing and structuring the data. Some of these mathematical operations can be applied to these data. These can be simple operations like subtraction, additions, multiplications of vectors present in the matrix. But others are complex mathematical operations such as basic correlation, classification, statistical prediction, optimization, inductions, and so forth. Here is a simple optimization mathematical structure, metaphorically called feed-forward neural nets. Surprisingly, many of these sophisticated formal models come from neuroscience, economics, psychology, physics, biology, information science, and so forth. And sometimes they come from pure mathematics. Some of them have been known for centuries. In the AI literature, many of these formal models are presented through some types of formal graph languages. Because of the remarkable marketing strategies of artificial intelligence, epistemic institutions, these formal models have been named metaphorically as neurons that learn, memorize, recognize, reason, decide, are intelligent, and so forth. But one can be sure that in a computer systems there are no neurons and they know and decide nothing at all. Such use of metaphoric languages in conceptual models only gives a small idea of what really these complex mathematical models really do and mean. But one must always recall that in a computer system, these are just formal mathematical models. We do not always recognize that the success of artificial intelligence rests on formal models. It is in their actual context of use that, if well defined, their semantic open up something to be understood. Let's now come back to our semiotic artifacts, the Magritte artworks, and the Pearce collected papers, and see how a formal model can be mapped on them and eventually deliver them some meaning. Recall here that our conceptual model had retained a number of features for each of Magritte's artworks or for each of Pearce's text segments. We had expressed these by various colored geometric forms. These will be the input data of our formal model. A first formal model will map on these inputs a formal structure that transforms them into two separate lists. The first one for the features is a horizontal list, and the second one for the artwork or text segment is a vertical list. A second formalization projects or maps a relation between each element of a list of features and each element of a list of artwork or text segments. It builds a database structure where each line describes for each artwork and text segment the presence or absence of a feature in it. This is expressed by the symbols yes or no. The next step is the real formalization. It is one that maps on these two lists the same relational structure, but this time the database is expressed into a mathematical language of vectors and matrices, where the yes and no become the symbols 1 and 0. Note that, semantically speaking, we have the same descriptions of the artifacts and their features. The whole matrix of vectors have become a set of mathematical statements. Such a formalization has now a huge advantage. For the manipulations of the symbols in this vector matrix, we can appeal to the whole set of mathematical operations defined in algebra, in linear and nonlinear geometry, topology, statistics, and so forth. We can now express these vectors of this matrix in some x-dimensional Cartesian space. For instance, we can see each artwork or text segment as a specific vector in the Cartesian space. Let's simplify this last formal model even more. These same vectors can be represented by points in a Cartesian space. We can easily see now a mathematical classification operation that can detect, for instance, how some vector points representing artwork or text segment are close to each other because they share the same features. We can now map each vector point into some classical graph structure. The line now just indicates iconically the proximity that was implicit in the Cartesian points. Now let's see the role of computational models, which, as we shall explain, is quite different from a formal model. A computational model is a special type of formal model. It is one that imposes on a formal model some specific constraint. It cannot retain all the relations or structure that a formal model could map onto some phenomenon. Only a specific type of relation is acceptable in a computational model. They must be functional relations in the mathematical sense of function. That is, the functional relations are a special type of dependency between the elements retained. Indeed, a relation is said functional between two sets of elements if, for each element in the set A, it is possible to calculate recursively what is its specific and unique element or image in the set B. For example, in a set of children, a son or daughter can only have one father in a set of men, but a father may have many sons or daughters. So only the former relation is a functional one. How then can this functional relation guarantee that for each son we can associate or map his father? That is to say, in more general terms, how can we guarantee that for each x in a functional relation there is an x that can be calculated? Despite its apparent simplicity, the problem of calculating function is one of the deepest problems in mathematics. It was Turing who gave the definite answer. It is called the Turing thesis. This thesis states that a formal expression is a calculable function if and only if it can be computed. That is to say, if it can be processed by two types of machine. The first one, that Turing called an abstract automaton, or machine A. This machine A is one that deconstructs the formal expression of a function into a sequence of instructions or rules. The second machine, B, is a mechanical one. Its role is to transform these rules into effective or concrete mechanical procedures. For Turing, this machine was a set of wheels, paper rolls, pens, and a set of printed symbols on papers. Thus, a mathematical function was said to be calculable if it could be computed, that is to say, effectively processed by an abstract machine and a physical mechanism. Many mathematicians demonstrated that Turing's abstract instruction could be translated into many other types of effective mechanical procedures. But it was not until 30 years later that Markov demonstrated that this computation could also be done in a set of procedures called algorithms. All the many other proposals were seen to be equivalent to the Turing thesis and to the algorithms, and this was summarized in the so-called Church-Turing thesis. This thesis essentially states that all these procedures, and mainly the algorithms, are equivalent. There are all effective procedures for computing a formal functional relation. This is ultimately means that a computer cannot compute anything else than functional calculable functions. This is the core job of computers. And this is what makes computational model so different from formal models. In other words, it specifies what type of formal models can be casted on a phenomenon so that this formal model can be eventually computed by algorithms. Unfortunately, there's a small problem with this computational model, and we cannot elaborate here on this problem. We can only recall its main statement. Not all well-formed equations expressing a function are computable. In fact, as many theorists will point out, this non-computability is ubiquitous. It is omnipresent in natural science and even more in engineering sciences. One can guess how it will be the case for computational semiotics. The solution offered by Turing was that if one encountered a non-computable function, it could be replaced by what he called an oracle, or that what is called today a heuristic, that is, an ad hoc solution. Here are a few examples of such functions. Take the functions expressed in the left part of the slide. These equations seem well-formed and intuitively easy to compute, but it has been shown by mathematicians that they are not computable. The ones on the right is pedagogically useful. There does not exist an algorithm to compute the number of tiles of such irregular shapes to cover a particular area like the one designed. In other words, for many mathematical functions, there are no algorithms. These non-computable functions are not the exception. They are in fact infinitely numerous. That is to say, their number is 2 at the power infinity. And the computable function, that is, the ones that a computer can compute, are just a subset of the infinitely huge universe of non-computable functions. We represent here these computable functions, but this very small point at the right side bottom of the slide. Still, these computable functions are themselves an infinite subset. But what is important here is to see that the relation between these two types of function are a relational probabilistic one. Indeed, for some problems, it seems more probable to find a non-computable function than to find a computable one, because the former is infinitely larger than the latter. We see, I hope, the consequence of this problem for a computational semiotics. Nothing guarantees that a computational project will find the pertinent and rich computable formal models, that is to say, the mathematical structures, that can be mapped or projected on some semiotic artifacts or a semiosis process. According to many computer scientists and semioticians, this is the case of what has been called the barrier of meaning problem, or what Eco formulated more radically as the wall of meaning problem. It still does not mean that there is no place for a computational functions. In fact, there is still left an infinity of computable functions. And if we lack some, it is also possible to use oracles, heuristics, ad hoc solutions. But this shows the limits of computational semiotics. It ultimately means that the computable functions that a computational semiotics will retain in its analysis will never cover all the complexity of semiotic phenomena and processes that humans invest in semiotic artifacts, because we cannot always project or map on them the computable mathematical structures. Let's now come back to our Magritte and Peirce's examples and see how we use some available computational models. Recall here that our formal models had mapped onto the semiotic features of the Magritte artworks and Peirce's textual segment an n-dimension matrix, and we had applied some mathematical functions on it. We present now a few results of the algorithmic translations of some formal models. Our matrix is here a basic formal model, but contemporary research in digital humanities, inspired by AI models, explored a myriad algorithmic applications on this matrix. All of these various types of matrices, sophisticated algorithmic mathematical structures can be applied. They go from subtraction, addition, multiplication, to correlation, classification, predictive probabilistic optimization, inductive operation, that build latent semantic spaces, random indexing, tensor-based spaces, distributed semantic spaces, and so forth. More lately, embeddings, transformer, and tension models have become the most popular ones today. And many of these computational models are now available in commercial and open source applications. Many are even free. On the Magritte matrix of features by artwork, we have applied a classification or clustering algorithms. It identifies 20 classes of artwork or set of similar Magritte artwork. Here we have a sample of 5 classes of these artworks. We give a name to each class. This name explicitates the theme or topic that characterizes each class, such as masonry, horse riding, female nudity, dressed man, pipe, and so forth. These topics vary in density in each artwork as it is shown in the lower graphic. We can take all the classes of Magritte's females artwork in the whole corpus, and we extract a list of the main features they share, as it is shown in the list on the left of the slide. From this list, an algorithm constructs a thematic signature of these female artworks by choosing some of its main features. For instance, we will find that the thematic signature of the woman artworks will be nudity, face, breast, pubis, navel, hair, sky, etc. The men artworks also have their own thematic signature. It's about jackets, collars, ties, ears, shoes, hat, and so forth. Now, if we compare the two thematic signature, we see that women are mainly presented nude by their breast, pubis, and so forth, and sometimes mutilated, bleeding, and kneeling, while men are presented standing up, well-dressed in bourgeois position, and sometimes with or hidden back view, empty faces, and so forth. One can imagine now how these results for art historians and critics open up a second-level interpretation. Many other similar and interesting such types of algorithms can be applied, and all invite a human interpretation. I have presented here just a few of some well-known AI deep learning algorithms on Magritte artworks. I hope this gives an idea of what a computational model can achieve for enriching one's interpretations of Magritte art's work. Our second type of experiment applies similar formal and computational models, but this time they aim at analyzing the concept of mind in the collected papers of Alexander's peers. Our main hypothesis is that a canonical concept manifests linguistic regularities traceable by classifications algorithms. We present thereafter the main core steps or workflow of a computational model applied to these texts. In summary, we build an algorithmic flow that first builds a concordance, which in turn is translated into a matrix, where vector lines are all textual segments of the concordance, and the columns are the n-words of the concordance. It is on this matrix that classical, either corpus linguistic or artificial intelligence algorithms are applied. Here is an example of the Peirce's concordance for the term mind. On this concordance, we apply some cleaning operations and we accept some morphological variants like mental, mentalistic, mentalism, and so forth. On the matrix of the segments and words, one of many clustering classification algorithms identifies which vectors represent the text segments of the concordance that are the most similar one to another. A formal classification mathematical model called K-means delivered 14 main clusters of segments. In other experiments, we explored the LDA, or the Latin Dirichlet allocation, which gave practically the same set of clusters with certain variants. Here is a sample of some 7 text segments contained in the cluster number 1. Please don't try to get the content now. Classically, a word cloud is offered. It gives a rapid hint at the thematic of the cluster. We see that most important words are mind, law, association, mental, matter. But as one may guess, such a bag of words cannot open into a deep analysis of the concept of mind. Still, it gives a hint what the concept of mind is about, and it will be questions about mental associations, laws, and so forth. Here starts the real serious analysis. Unfortunately, for the moment, it is in part handmade, but the labor is diminished as the role of the research is mainly to annotate to each segment with either a discursive, a categorical, an argumentative definition category tag. Contemporary artificial intelligence research and strong natural language computational models are a possible assistance for this step. Certain chat box model could be helpful here. Here is a set of text segments that are annotated as being epistemological explanation segments. For each class identified, an algorithm recuperates the various sets of annotated segments. For instance, the definitional segments, the explanatory segments, the illustrative segments, and so forth. With these segments, the analysis rewrites a set of comments by using the various phrases discovered in the cluster. Summarized here is the result of the work on the cluster number 1. We can read the synthetic rephrasing of as expressing the thesis that, for peace, the laws of mind are associative. It is a form of synthesis operation. It is difficult to observe, etc. The number in the text indicates the original text source. The same process is applied to all other clusters. For instance, the interpretative comments of cluster 2 states that mind, despite its various meaning, is a structured semiotic process, and the science that studies its semiotics because it pertains to the manipulation of signs. Here we have an interpretative comment for the cluster 3. It states that consciousness is an essential feature of mind. It is not an entity. It contains feeling, willing, and knowing. And this synthesizing process goes on for all the other clusters. This allows to produce an overall synthesis of the concept of mind. We would state it summarily this way. The mind is a dynamical semiotic system. It operates on sign in an associative manner. And consciousness is a fraction of what thought is attentive to. It presents psychically thought, feelings, will, and knowledge, etc. We oversimplify here the synthetic interpretative comments. Technically, it is just the aggregation of all the interpretative comments of each segment of each cluster. Our fourth models in a computer models is one about the computer itself. The role of the model here is to define how the algorithms retained are effectively implemented in a technology, here an electronical technology. Since ancient times, it was possible for some humans to calculate concretely complex mathematical functions, such as the ones on the screens. These humans, though, were special. They were called scribes, whose task was to calculate by hand and stylate those functions. Later, these scribes were called computers. But the computation of these functions, even with simple appearance, could take months to be actually calculated. Way before electronic computers, there were some mechanical machines that were capable of calculating computable functions. The best known ones are the abacus, the Pascaline, the Babbage machines, etc. Time does not allow us here to deepen the complex nature of the physical architecture of these electronic computing systems. It is a complex theoretical problem to identify the various components that today allow the variety of the material forms that are the transistors, the Wi-Fi, the cloud, the disk, etc. But one main and important characteristic is the processing speed of these components, and also the iconic interaction with humans. They are the ones that today allow efficient, concrete, computational semiotic projects. Let us conclude. I hope that I presented computational semiotics as a serious epistemic endeavour. The project that it builds rests on the constructions of many interrelated and differentiated models, all of which participate in the analysis and the interpretations of semiotic artifacts and semiosis processes. But because of the nature and the complexity of these semiotic phenomena, mainly the barrier of wall of meaning, mapping or projecting on these phenomena, formal and computational model, is not an easy task. And the algorithmic workflow is not always itself a purely computable process. Interpretative decisions must intervene all along the process, be it on the input data, the choices taken in the formal computational and physical models. And we must underline in this workflow the importance of the conceptual model. This model is the ultimate grounding of all computational workflows and processes. It constrains the other models, but mainly it offers the interpretative horizon of the results, and it embeds them in our understanding. And this conceptual model may itself take quite a long time to attain maturity. In this view, a computational semiotic epistemic endeavour cannot be an artificial automatic semiotics. It is much more an adjuvant in a deep interpretative or hermeneutic understanding of semiotic artifacts and semiosis processes. Thank you very much for your attention.
Well, thank you very much, Professor Meunier, and thanks also to Gabriele for helping get the presentation back halfway through there. Well, there was a lot to think about there and a lot to unpack from that presentation. And to help us begin to do that, we have, I think, 6 panelists who are going to make a short response to what we've heard today. So I'll introduce them as we go along. So the first person I'd like to introduce is Dr. Michael Meunier, who has woken up very early to be with us today. He is an ophthalmologist and anthropologist based in Timaru in New Zealand, and a specialist of face-to-face interaction. So Michael, if you'd like to begin.
There, never mind. Yeah, okay. Thank you very much. I have stayed up very late for this, and I also got hold of your book, Professor, and so I've been doing some background reading, and so I hope to be able to comment more fully when it's not 4 o'clock in the morning or 5 o'clock in the morning, when I've had time to digest all this. I have met up with medical modeling as well as the kind of modeling that people do when they are in conversation. And so medical modeling is quite paradoxical in that you would think that it would be a straightforward thing and there would all be indexes in Peirce's sense. But there has been great difficulty in deciding what medical concepts are, and it's still an unsettled question. So that's an interesting dimension on it. From your talk, the thing I really didn't know was about this concept of projection on the world, which you mentioned the name of Bourbaki, and you also mentioned that Peirce talks about projection. In my work with text analysis of conversation, projection was very important to me because I reckoned that I could understand intonation by thinking of the people throwing themselves forward and then pulling themselves along to get to the position that they had thrown themselves forward into. And so for me, conversation was a matter of alternate projections, projection. And I argued that was a dimensional matter. So I'm going to look with great interest at this concept of concepts themselves being projections onto the world. Well, it's late for me, and also we're running late, so I won't say more at the moment. But thank you very much, and I'll be saying more when I do the formal response. Thank you.
Thank you very much. So next up, we have Dr. Ken Foot, a geographer from the University of Connecticut.
Thank you. I enjoyed the presentation very much, and I found it interesting because I had the good fortune when I was in graduate school at the University of Chicago years ago to have as an advisor one of the early innovators in computational linguistics, Victor Ingve, who was the head of the MIT Machine Translation Lab early on. And it was interesting then in looking at the developments since then, and I appreciate the advances that have been made. I was interested though, because I know Professor Meunier's work, and I'm curious in reflecting on what was said today, that what he learned about the differences between the sort of linguistic modeling and some of the points that he raises about the modeling of the semiotics of pictograms and artwork and so forth. Because when we discuss these issues of models, I'm curious about how that actually works out in practice, because much of my work, even though I'm in a different field now, focuses more on the spatial arrangement of text, the physical nature of words and messages and so on, artifacts and icons and so forth. So I'm interested in, I guess, more detail about the way that we think about these models as we move into the visual realm and in other modes of communication. But thank you very much. It was a fascinating presentation.
Well, thank you very much, Ken, for that. The next panelist who we have with us today is Daria Arkhipova, who is a PhD candidate at the University of Turin. I think looking at semiotics and AI. Sorry if I got that wrong.
No, it's absolutely right. Thank you so much. And thank you so much for presentation. It was absolutely fascinating, especially I was caught by the idea of references to Markov's algorithm, which is one of the very curious ways of producing decision-making using artificial intelligence. And since I'm studying how artificial intelligence recommendations impact our decision-making, it is very interesting that it's very rarely used in the practice by the companies, for example. And it is very interesting also when you apply it to the purse, because I believe that there are various interpretations of purse, and there are several arguments during all the conferences how purse should be interpreted, and if we would have some formal criteria for that in the shape of algorithm, that would be amazing. However, in the process of interpretation, as in the process of semiosis itself, it's sometimes very difficult to say that something stands for something and not for something else, as you mentioned, that it's really up to the intention of the interpreter. So I find your book very interesting, and I hope that it would find other implementation in the, like in my research, and also in the business part. Thank you again.
Thanks, Daria. We also now have Dr. Martin Ulrichs, who is an archaeologist. He's at the Joukowsky Institute at Brown University. And yeah, Martin, it'd be interesting to hear your thoughts.
Yeah, thank you. So actually, no, doctor, I'm also a PhD candidate, but
Right.
nonetheless, yes, thank you very much. I mean, it was, you know, despite all the technical sort of was very difficult on my connection here. So I picked up fragments here and there, but what really did stand out to me was that in my main field, sort of archaeology, which falls within anthropology and the larger social sciences, is that there's, as you sketched out as well, in sort of the development of these computer science models, is this very sort of gradual growth in these theoretical ideas, starting with Turing and CS, but then also moving into the hardware developments in the 60s and 70s that really pushed the field forward into the sort of down the path of electrical engineering. And it's really in that path where things got stuck in this mathematical, systematic way of thinking, which very much in the social sciences and archaeology and anthropology at large, and sort of the social sciences at large really started sort of to take a hold as well, right? That's in the 60s and 70s and the 80s throughout. And what I find fascinating is that in the computer science world, as I mentioned earlier, I've got 1 foot in the computer science world and 1 foot in the archaeological world. And in the computer science world, people are recognizing, they're cognizant of the fact that they are stuck in that electrical engineering model. They're cognizant of it, they're aware, they acknowledge it, they want to wrestle with it, but they seem to lack the means of doing so. And what is fascinating to me is that even though they know of the problem and they are fully aware of all these, algorithms and sort of uncomputable, these problems that exist, they seem unable to sort of easily grasp the problem in that sense, to grapple the situation in a way. So I find it fascinating. In archaeology, we're only starting to really, in the last 20, 30 years, I think, we're really starting to grapple with the more human aspect of things. And I think you've really pointed out nicely that we really need something like that in CS if we are to try and bridge semiotics and computer science and possibly related STEM fields, if you will. And I think it's a larger problem that ties into how we educate, how we, where we build those bridges within the educational system that then allows us to move in the next generations, to move away from these very static ways of thinking that really go back to the 50s and 60s. But yes, thank you very much. And I haven't read the book yet, but I'm looking forward to it.
Fantastic. Okay, so we have 2 more respondents left. So next I'm going to call on Professor Hubert Kałuski from Marie Curie Sklodowska in Lublin, Poland. Sorry if I've got that pronunciation wrong. Who is a linguist and a literary theorist and a semiotician.
Yes, thank you. Thank you very much. Thank you for your very interesting lecture. I was thinking, and you touched upon that during the presentation, about this pragmatic aspect of representation, what makes something a model or a scientific representation. You mentioned Van Frassen, he popped out in a few places in the presentation, and it's this problem of how models are actually used, not just the some kind of formal structure of the model. So Van Frassen in one of his books says something like, okay, let's say you have a picture of the Eiffel Tower, right? But what if you scan the picture and you send it over the internet, and this digital image, is it a representation of the Eiffel Tower or the picture that you scanned, right? And Van Frassen says that, well, you can't actually answer that question on the basis of some kind of formal properties of the image. If you say, okay, well, I've sent you the picture of the Eiffel Tower. This is what Eiffel Tower looks like. Well, the scanned picture is a representation of the Eiffel Tower. But if you say something like, oh, this is I scanned and I send you the picture of this kind of image of a picture. This is what this picture looks like that I talked to you about. This is the representation. What you send is a representation of the picture. So this is the same object, right? But depending on whether you treat that as you want to use it as a representation of the Eiffel Tower or the picture of the Eiffel Tower, it's a representation of something else. So I was thinking about how this pragmatic aspect of how people using models make it one kind of representation or another, how it can be tied, how this can be tied into that. Although I think that popped up in the presentation a couple of times when you said that this mathematical formula are not just in and of themselves, they are not just models. You just need to tie these formula to some kind of real world thing, and this is what people do. This is what users do. So I was thinking at the back of my head about this pragmatic aspect, how you could tie all these computation to the idea that, well, ultimately model has to, in order to be a model or representation, it has to be used by someone in a certain way. But that's just like a side note, maybe some kind of interesting thread for future discussions. So thank you.
Thank you very much. And finally, we have Dr. Gabriele Aroni from Manchester.
Well, thank you, Andrew, and thank you, Professor Meunier, for the very interesting presentation. And my question is more about mathematics in general, because I never thought about semiotics and mathematics despite being used very often, maybe because I still have nightmares about my analysis exams. But is mathematics itself, even before being computed by a computer or an mechanical calculator, can it be a semiotic language, or is something that is asignifying by nature? I mean, it's always two means two, but it can be assimilated to a language. So is there ever going to be, even really theoretically, a way to have a mathematical model of any sort that is meaningful by itself and not necessarily a correspondence between a pre-existing sign or symbol that we have, like in literature or in pictures, and instead something that is meaningful by its own mathematical essence? I don't know if this is a clear question, but anyway, can mathematics being considered a meaningful language by itself, having a semiotic value outside of schematizing existing signs from images or text? And if that can lead to exactly an actual artificial intelligence that is more intelligent than what we have now. Thank you.
Thank you. So we are a little bit tight for time, but Jean-Guy, if you have anything you'd like to say in response to any of these points, please do take a little bit of time now.
Thank you very much for all your very positive and motivating comments. I will try to be very brief in my reactions to them. Most of you are interested in some specific semiotic artifacts or processes. For instance, Martin Meyer studies conversational processes in the medical field. Dacia Arkikova analyzes decision-making in business. Hubert Kowalewski underlines the roles of users in language, and Ken Foote is interested in how visual languages are meaningful. Martin Ulrich explores how meaning is embedded in archaeological artifacts. And knowing Paul Buissac's interest, he explored the semiotic processings of clowning. I believe that one important characteristic of these semiotic artifacts and processes is their complexity in the technical sense of this word. What that is, they all manifest a myriad of features and intricate relations. As Martin Ulrich noted, a strict computer engineering approach is not adequate for explaining and understanding these complex phenomena. And I said in my presentations, computers can only manipulate algorithms. This is their main job. But one point I've tried to underline is that for their part, the algorithm's job is essentially to compute calculable mathematical function. It follows then that the core of a computational approach to the semiotic artifacts will be the mathematical models. If there are no mathematical models, there are no algorithms and no computer processing, and therefore computational semiotic is impossible. What I felt, though, in the comments were the following underlying doubts or question. That is, can mathematical models and its algorithmic translation deal with the complexity of the chosen example presented in the comments? This is where the question of Gabriele Aroni is important. Why could mathematic models offer some adequate models, more so if they can be translated algorithmically for analyzing and understanding complex semiotic processes? Answering this question will take more than 2 minutes. But the first step to be taken in answering this question would be to see if mathematics have any relations with the semiotics and vice versa. This is where Peirce's analysis is, as is often the case, highly heuristic. All through his career, he constantly repeated that mathematics were a semiotic system. That is to say, mathematics are structured sets of signs that can be manipulated in and for themselves. This is just another way to say that mathematics builds formal systems. And it is here where Peirce's pragmatic view is interesting. For Peirce, mathematical signs acquire meaning, that is, their interpretant and their object, through their use and their intentions of the interpretation. More importantly, Peirce's philosophy of mathematics, as many contemporary commentators underline it, mathematical statements are not to be understood in a realist perspective. They are hypotheses generated by imagination, in that it is imagination that maps a relation on world of possibility. They do not reflect as such the existing ontology of the world. And it will be the role of observation and experimentation to see if these imagined mathematical statement or hypotheses are true or false in regard to some actual world. Finally, in the case of very complex semiotic processes, only a subset of these mathematical signs can map or project some specific properties, features, or relations on the object under study. And only a subset of these properties, features, and relations will themselves be input of computational model. Although mathematical and computational models may produce highly rigorous explanations of some specific dimensions of semiotic artifacts and processes, they will offer only limited understanding of their complexity. And this is why conceptual models will be so important in computational semiotic projects. It is in conceptual models that an ultimate understanding emerges. And this is because conceptual models embed formal and computational models in intentions, context, situation, cognitive structures, consciousness, personal experience, social sharing, ethical values, and ultimately culture. One may guess it is in conceptual models that semioticians will be at their best in any computational semiotic projects. But this is also true for many artificial intelligence projects on meaningful or semiotic artifacts and processes. But if semioticians do not invest seriously in these conceptual models, whatever the type of formal and computational model they are involved in, one can be sure that computer scientists themselves will take over this task. And this will be surely to the detriment of the meaning involved in these artifacts and processes, and ultimately to semiotic itself. Thank you all for your fine attention and serious listening to my essay on computational semiotics.